Today we have Professor Lindsay LeBlanc from the University of Alberta, Edmonton, where she is currently a Canada Research Faculty or Professor. But equally important, she in fact did her postdoc at the JQI, at the sort of NIST arm of the JQI, leaving in 2013, which seems like an amazing thing because it was like yesterday today that Lindsay was doing her postdoc with us. Since then, she's gone off and set up her own lab and had her own results you're going to hear about today. Furthermore, she's going to be around for the rest of this afternoon and, of course, lunch if you'd like to meet with her. She'll be doing lab visits in the basement, probably starting around 2 o'clock or so. And as always, at 4 o'clock, there will be tea with the students. Wendell, what room? Okay, I could have said that. At the usual. Something Atlantic. All right, so thanks everyone very much for showing up. And if anyone's online, I hope it's working for you. And here you go, Lindsay.
Great. Let me clip this on, I'll see if it works. Okay, well, thank you all for coming, and it's a real pleasure to be here, and thank you for the invitation. I haven't actually been back to Maryland since I left 10 years ago, so it's kind of nice to reminisce a little bit. So I'm going to talk today about some of the work from our lab, in particular in quantum memory, which is the title here of this slide. Try this remote, just different kind of pointer here. I'll also talk a little bit about other things if time permits, but we'll see how that goes. So like Ian said, I'm currently in Alberta. I'll just show you where that is. I was doing some reminiscing. So this was in 2011, it says here. I found the date. So we had Retrophysics Day one day at NIST, and we all dressed up as if it were some time ago. So this was me and Ian and the other postdocs and graduate students in the lab at the time. So Ross and Karina and Matthew Beeler, me and Ian there. And I also remembered that I got to give this seminar also 11 years ago when I was a postdoc. So it's a bit reminiscing. So I'm in Edmonton, Alberta, Canada. Part of Treaty 6 territory, so we're way up here, and I think we're the coldest city in the world that has cold atoms. So that's a little bit of a claim to fame. I guess you could say we get a bit of a head start. So only a little bit though. But in seriousness, Edmonton, it's also one of the largest cities this far north. So we're a city of 1 million people. It's a nice place to live, and it's actually I'm from Western Canada, so it's home to me. All right, so here's my group from the summer. Not everybody's here, and so on, but it's in 10 years it's been fun to build up a group, and I just want to show them first because of course these are the people actually doing all of the work in the lab, and it's been a real pleasure to be able to work with them and mentor them over this time. So I don't think I need to convince you all of this, but we basically do things with neutral atoms in my lab and all kinds of different things. And the reason that they're so nice is that they're these readily controlled quantum objects. And so we can do, when I'm trying to sell what quantum is to people, the fact that we can, think about superposition and entanglement is sort of the quantum technology aspect. And they're also very sensitive to electric and magnetic fields. And the point that maybe I'll make for this crowd is that one nice thing about it is that we have access to 2 different kinds of transitions. We have probably more, but these are the 2 that we use. These strong and short-lived transitions, or the optical transitions that we use for things like laser cooling, and also for doing some of our control. And we also have these weak and long-lived transitions, which are magnetic dipole transitions. And that means that we can directly address them, which we do in some of our work, or use them for our quantum memory states. So we do a few different things in the lab, as I mentioned. I'll talk mostly about quantum memory today. So in this scheme, we sort of leverage this level structure where we have these short and long-lived transitions, so we can do fast operations with optical, but actually use the 2 ground states as our storage basis, and that's a nice thing about atoms. Another thing that we do in the lab is work with sort of microwave atom optics. So we have these microwave cavities that are the size of my fist, and we put vapor cells of warm atoms inside, and there we're leveraging both these microwave transitions, which we can amplify with the cavity, and also the optical transitions, which we can access simultaneously. And then finally, we also do some work with more along the lines of many-body physics, although we're not actually, we use it more of as a single quantum object, but we use BECs with microwave, RF, and optical fields all together to do sort of quantum control and look at interesting quantum states, including some work with a geometric phase that maybe I'll talk about a little bit at the end of today's talk. But I like to sort of tie it all together. Basically, you know, we use the same tools to do all of this kind of work, whether we're looking at the fundamental physics or more practical applications. And it's all about these optical and microwave transitions in the lab. So yeah, my lab, we basically use rubidium-87 BECs, the workhorse of this field, to do this kind of quantum memory work. Sometimes we use BECs and sometimes we use not so cold atoms, but still cold. And I'll talk about two kinds of quantum memory that we've been working with. One we call the Autler-Townes memory, and one is sort of a faster superradiant memory. We also do this state control, so we'll talk a little bit about that, and these microwave atom optics. So actually, I'm meant to delete that slide. I made a new one last night, but here we go. So we'll talk about the quantum memory first. So in this atomic quantum memory, yeah, like I mentioned earlier, we're going to leverage these strong optical transitions. And this cartoon, maybe I'll talk about here, the basic idea of the memory is that you have some kind of quantum state come in. I don't know, yeah, it should be T1, look at it. But the quantum state comes in, it's some kind of information encoded in light. Likely that would be time bin polarization or time bin qubits in the kind of work that we do. But one can also think about polarization, encoding of information. Or maybe something that's slightly more exotic. But the nice thing about the atoms is that you have this storage medium, and the idea is that you send the signal in, you can hold on to it for some time, and then get that signal back out at a later time. So a fairly sort of simple component of maybe some kind of quantum technology. And the kinds of things that we're thinking about are related to maybe the quantum internet. So you want to send some signal from point A to point B, whether that's for a QKD kind of protocol, or you want to distribute entanglement between locations, whether that's through fiber or through a satellite link. We need some way to get information from point A to point B. And so one of the key components to make that a real practical technology is the quantum repeater. And that's because there's a lot of loss in fiber and even more loss through the atmosphere if you send signals. So 0.2 dB per kilometer doesn't sound so bad, but if you start going over many kilometers, that's limiting. And people have calculated that, say, more than 100 kilometers is sort of impractical. You need some kind of quantum repeater. But you can't just have a quantum amplifier, so you can't just put a Q on an amplifier and say it's going to work because of the no cloning theorem. So you have to do something different. And the sort of proposal that people have come up with, sort of, you know, back in the 90s even, was that one can distribute entanglement through elementary links. And there's many different components to that, but the quantum memory is sort of a key one if you want it to work in a practical situation. So the idea is you have some kind of twin photon source that sends out entangled pairs of photons. You can send one locally and one over some distance through a fiber, and you do that in different locations. So each box here is a repeater, and then you have some link that links them together. Those photons are entangled, so you can then entangle, you know, send it into a quantum memory, entangle it here with one that is far away. And you do that, so you have now, you've distributed your entanglement, but so far that's sort of limited in scope. But the next step is to do a Bell state measurement locally on those two entangled photons. So now you've distributed the entanglement over a longer link. So now you've gone sort of 2 units, say 200 kilometers. And then you can do that again. So now you can do a Bell state measurement here in the middle, and you can distribute your entanglement from there to there. So the sort of sequential process is a way to get quantum information over longer and longer links. This is, of course, a difficult problem, and it's only recently just been demonstrated in theory in a few different places. Trapped ions and nitrogen vacancy center demonstrations over the last couple of years, both in Delft and Innsbruck, have been really impressive, and other smaller scale things going on as well. But you need a lot of different components for this to work well. You need efficient single photon or twin photon pair sources. It's not something we're necessarily working on, but the quantum memory is actually a nice and an important part of this just for synchronization. So if you want to do these Bell state measurements and have your photons overlap on your detectors, they have to arrive at the same time. And so you want a quantum memory that you have a lot of control over, that you can release the photons on demand and have them you know, synchronized so you can do this Bell state measurement. The other, you know, caveat with this is that these photon sources are often probabilistic, and the quantum memory turns a probabilistic source into a deterministic source. You can wait until you get your entangled pair, have some herald, and then release it when you get it. So it increases the efficiency of the possibility. One could, if you had deterministic single photon sources, maybe you could skip the memory, but it also allows for this time of flight between different locations. So then if you have two memories that are local, now you can do the synchronization nicely. So this is one of the sort of maybe near-term applications of quantum memory in a place where atoms might have a chance of actually contributing, because the kinds of storage times that we're talking about here are sort of many microseconds to millisecond scale, and that is very much feasible with atoms. So, quantum memories are not a new idea, and I wanted to, this list is not exhaustive by any means, but there are many different ways that one can make a quantum memory, ranging from a lot of nice work with warm atoms, the kind of cold atoms work that I'll talk about today, but also things like ion-doped solids, and even color centers in solids as well. And there's actually even things like fiber loops, which I haven't drawn on this slide, that all can be used as ways to store this kind of quantum information. And so, of course, as with any quantum system, there's different advantages and disadvantages to each of these platforms. Cold atoms that we use are very nice, but of course, the infrastructure behind these is bulky. And so how practical these would be, one can see, but I mean, technologies are all moving forward. So we're pursuing this at the time. The other aspect is not just the platform one uses, but the protocol. And there's different ways to do quantum memory. Usually they either rely on a kind of adiabatic elimination or absorption. So the adiabatic memories, usually one thinks about EIT kinds of processes. So you have a three-level system, the kind like I drew before, and you have two optical beams, and then your storage comes about between a coherence and these ground states. And this is what I'll talk about a little bit later. You can use EIT, where you have a real dark state, so you're not exciting anything into the excited state, and so it gives you a very efficient memory. You can also do off-resonant things, and that gives you a faster memory, but has some noise issues. So notably, Alexei Gorshkov's papers from his PhD in the Lukin group are very useful. They kind of explain the whole gamut of these adiabatic and non-adiabatic memories. And that kind of theory is sort of used throughout the community now. There's the other kind of memory is a fast memory, and it uses direct absorption. And this is the kind of memory that's often used in the solid state, for example, the rare earth ion-doped solids. And here you can think about, individual quantum absorbers and emitters that have a phase, and you excite these all together in phase. They might decohere, and often what you're doing there is having them sort of absorb, they evolve, and then they rephase at some time. When they rephase, they emit light, and that is your signal out. And so there's different names for these things with different acronyms, but like GEM, gradient echo memory, I know is one that people have pursued around here. So it is also very efficient, but it isn't necessarily able to give you a signal on demand. So the rephasing time is often imprinted into these things. And so you have to kind of time things according to that rephasing time. So when you're considering a quantum memory, what do you want? Well, there's different axes and different kinds of memories which are good at these different things. Efficiency is very important, of course. So what probability do you have that the signal you have coming in is what you that you're going to get it out again? How long can you hold onto the signal? Like I mentioned earlier, you probably want at least millisecond kind of timescales for the times of flight between, say, 100 kilometer fiber link or between the ground and space. And that's probably, in order to be useful, you need to get to that scale. And then the bandwidth of your signals. So you want to be able to match the signal bandwidth with what kind of source you're using. And the issue here is that many single photon sources are quite broadband. It also determines how much speed and how much information you can handle. And then finally, noise or fidelity. And the question you want to ask there is that, are you sure that the signal that you're getting out is actually the information that you put in? Or is there actually noise coming out? And that can be an issue with some kinds of memories where four-wave mixing, for example, can be very detrimental to the signal.
You have a question?
Sure. Yes.
Great memories which like deliver your state of flight on demand, or you think that needs to delay it for some time?
So both. So I would say that both of these can be can do both, but typically the adiabatic kinds of memories are on demand. So you have a control which you store it with, but also then it lets you get it out on demand. And a lot of these fast memories are timed, so that yeah. Although there are ways to sort of shelve information in the fast memories, but then you have some dead time. So there's sort of trade-offs on a lot of these things. But yeah, both are sort of possible here. So yeah, any other questions? This is sort of the end of the background. So what we did in our lab is sort of found ourselves in a different regime than had been really explored experimentally before, where we're actually combining aspects of both these fast and slow memories. So this is sort of, we've found ourselves at the intersection between these two, and turns out that you're in the Autler-Townes limit of coupling. So we've given it this name, Autler-Townes protocol, where you actually get a lot of benefits. So it's fairly broadband, it's very low noise, it is an efficient memory, and it is in principle capable of long storage times. So I want to go through how this works in the next few slides here. So going back to the basics, what do we want to do? We want to take a state of light that's encoded in the photonic degrees of freedom, where we sort of start with an empty atomic state and transfer it. So how do we do that? We're going to use the 3-level system, and this is really the bread and butter of what we use in our lab in a lambda configuration. So we'll just give these the ground and auxiliary states, both ground states and some excited optical state here. So these are, forbidden in the electric dipole sense, but that makes a nice storage state because in principle, these can be very long-lived as long as there's no, some kind of dephasing going on. So this is going to be our storage state, and that's where we want to store the information. I'm just thinking about a single atom at the time, but we'll talk more about the collective nature of this later. Then we have 2 optical transitions. We'll call one the signal transition and one the control transition. Here in our case, the control is very much classical, so we'll just give it a Rabi frequency, whereas the signal transition can be a real sort of quantum optical field. And we can think about these separately. And so what we actually want to think about is not the populations of these levels, but the coherence between them. So we have a polarization coherence between this ground and excited state, and that really, and I'm explaining this to, say, undergraduates, I say this is like a measure of how much superposition there is between the ground and the excited state. And we can quantify that with this operator here, which is a projection from excited to ground and the Hermitian conjugate as well. And then we also want to consider the spin coherence. So that's the superposition between these states. And that's sort of our storage. So how do we have coherence between these 2 states? And the thing that's connecting them is going to be this classical field, which is our control field. And so we can think about that as sort of a Rabi, Rabi process that's happening there. And so, there's a nice set of equations called the Maxwell-Bloch equations that describe all of this, where we can relate the input electric field, so that's on this transition, to the polarization. So the electric field coming in creates a polarization coherence. The dynamics of the polarization coherence depend on itself, this electric field that's coming in, and also through the Rabi frequency, the spin coherence, and then vice versa, the spin coherence depends on itself and the polarization coherence because it's not directly connected to the electric field coming in. And so these are, some nice equations. We can plug them into MATLAB or Python or whatever and just solve directly. But it is evocative to simplify things a little bit and see what happens here. So if we work in the limit, first of all, where the decoherence is very small, so we're actually going to work where there's basically no decoherence between the spin levels. So let's just say that's about 0. And we're also going to work in the limit that is resonant, so there's no detuning, and where the decay, this is the decay from the excited state down to these ground states, is going to be much less than the Rabi frequency. So this is where the Autler-Townes bit comes in, is that this Rabi frequency is greater than the spontaneous rate of decay. And so what we think about is that these terms can then drop out of our equations, and we're left with a simplified version. So really, these 2 equations are the sort of interesting ones, where we see that the polarization coherence depends only on the spin, and the spin depends on the polarization coherence. And this set of equations is very much the set of equations I teach to my first-year students when we're talking about the harmonic oscillator. So we just have exchange between the polarization and spin. And if we want to think about this from a sort of mechanistic level, what's going on here is that we sort of establish a polarization coherence. We can establish it with the electric field. Once it's established, what's happening is that sort of the population or the amplitude in the excited state gets Rabi flopped down to the spin level. And so what we're really seeing is now not a Rabi flopping, well, we see a Rabi flopping between the excited and S levels here, E and S. But what that means is that there basically is a Rabi flopping between the polarization coherence and the spin coherence. And so I can make a cartoon of that as well. So when the electric field comes in, it excites the polarization coherence, and then at half a period in units of this Rabi frequency later, we've exchanged from polarization to spin, and then it just is going back and forth. And this is of course where there are no losses, so it's just unit efficiency back and forth. So what we're really driving here is a Rabi flopping between coherences as well as between the amplitudes of these states. That's great. We can do more precise calculations by adding in some of these spontaneous emission, and well, we still eliminate the ground state decoherence. But how do we turn this into a quantum memory? Well, this is sort of like a fast memory where we just leave this dashed blue line represents the Rabi frequency. We leave it on all the time. And here we're in the regime where the control power is 7 times the decay rate. So we sort of send in this light pink is the electric field coming in. And what that does is it establishes, I'm sorry, these are in different order than the previous slide, but it establishes a photonic coherence, which establishes the polarization, which then Rabi flops to spin, back to polarization, and then back and forth. And you can see this decay times about this factor of 7 that we've built into these equations here. So what happens is that field comes in, establishes a polarization coherence, turns into spin, turns back into a polarization, and once we've established the polarization coherence between the ground and the excited state, that's an electric dipole moment, and it re-radiates. And so it's a little bit like rephasing of the dipoles in the solid state kinds of fast memories. We've rephased, the light is emitted, and some of that energy goes away, but then the process continues. And we can see sort of revivals of that electric field coming out. So you can see one little bump in the simulation, but most of the energy actually comes out in that first one. So did you have a question?
So there are 2 time scales, right? There was like this G square root N and then the Rabi.
Yes.
And they're operating in a regime where G square root N is faster.
So the question, yeah. So the question, there's the G square root of N. So if we go back to these equations here, yeah. So the G square root of N is the question is G square root of N bigger or smaller than the Rabi frequency? So this is very fast, yes. So we have a large number of atoms and we get a collective enhancement. And so that N, yeah, N is very large in this case. So again, I didn't talk about that scale, but yes, this is large, and then this one, and then the decay would be the smaller scale yet to that. Okay, so this is the sort of idea of just a rephasing of the memory, and this is actually from the sociological perspective. This is how we started in the lab. Was that my postdoc had worked on the AFC quantum memory, one of these solid state quantum memories, and he sort of wanted to learn about cold atoms, came to the lab, helped us make our first BECs, and he said, hey, I wonder if I can make an AFC kind of memory using atoms. And so that was his goal, and he thought, well, an Autler-Townes splitting is a lot like a 2-comb atomic frequency comb, or a 2-spike atomic frequency comb. And there's that, basically this, you can think of, I didn't have these pictures here, but the frequency, the splitting of the excited states is given by the Rabi frequency. And so that sort of sets this rephasing time in this memory. Okay, so this is, not on demand, but we can make this on demand by just turning off the control field now. So this sort of harkens back to the EIT adiabatic kind of memories where you have your control field on, and what you do is you leave it on. You need your timing to be pretty good, but you leave it on while you send in your field, and then you establish this polarization coherence. And once that polarization coherence sort of flops into the spin degree of freedom, you turn off your control field, you wait for however long you want, and now you have an on-demand memory. And the equations basically just restart once you turn the control field back on, and then you get your sort of rephasing happening later. And so this allows you to do an on-demand memory, but you can do it quite fast. Yes.
So you started to touch on what might be the usual conception of what Autler-Townes splitting means.
Yes.
That is that there are two states that are split apart by an amount that's proportional to Rabi frequency. What I'm wondering is there something in the fact that there's empty space in between those states that is working to your advantage in terms of not exciting stuff that you might normally excite, or are you just losing stuff at the rate of a seventh, whatever the Rabi frequency is, no matter what?
So we are going to be losing coherence at that rate. The gap in between, so you're right. Actually, I think I have some slides about this later and we can come back, but you can think about, I can draw to you, but you have your sort of Autler-Townes splitting and your signal actually spans the full width. And there's some efficiency arguments that you should actually have a particular spectrum that covers your Autler-Townes splitting nicely. And to get the efficiency, so that gap, you actually do want absorption at all frequencies, right? And so in practice, the most efficient sort of pulse sequence is actually, you start with the splitting closed, you sweep it open and sweep it closed. And so you actually cover all frequency components throughout the process that way. So I think that's actually a little bit in the next slide. It's hidden in the calculations as well. But a nice thing about this memory is that it's a pulse area based memory. So as long as the time integral of your Rabi frequency meets in the units that we use 2 pi, a 2 pi condition, you sort of you get the full transfer from one state to the other. And so you can do some sort of pulse shaping with this, and turns out that works better. So if you think about a Gaussian pulse coming in, that the timing of that Gaussian is exactly such that you transfer all of your coherence into the spin degree of freedom. Then when you have your pulse come out, you can actually sort of shape it so you get more energy transfer into the photonic degree of freedom on the way out. And there's of course some optimization schemes that one can use to help with that.
So what I was thinking about was that when you do EIT, you get that dip there.
That's right.
And then as you crank up your control field, you make that dip broader.
Exactly.
And at some point, it sort of continuously goes over to an outlet.
I think that's my next slide. Yeah. So exactly. And when you first started doing this, there's a lot of questions like, is this different than EIT, or is it the same thing, or what's going on? And so we actually wrote a PRA. This reference is on the slide, trying to explore, numerically, especially what is the difference between all of these things. So here's the EIT picture I think that you're talking about. So and note that the frequency. So here's my frequency scale here. So the frequency units are very different on these scales. So I go from a very narrow frequency band to bigger ones over here. So the sort of traditional EIT memory is in this regime where you have a narrow window that you usually think about associate with EIT. You have this narrow transparency window, which gives you a very steep dispersion, and that gives you this slow light phenomenon. So usually with an EIT memory, what you want is you send your signal in, it becomes so slow because of slow light inside of your gas, then you turn off the coupling and you've parked it in the gas, and then you can turn on your coupling again and it slowly goes back out. The thing, with that, and that's sort of represented in the time domain picture here. So your signal comes in, sort of slow down, and so that's just storage, or you can sort of do this on-demand thing where you have some ramp. So this is just a simple ramp. You let your signal come in, it slows down, you turn it off, and it comes back out. You'll note with the EIT that there's no polarization coherence. So this is the aspect of the dark state. So you never actually have any population or amplitude in the excited state for EIT. And so that's the difference. Next, if I jump to the far end of this, this set of graphs here, this is what I've been talking about as the broadband ATS. So this is the kind of frequency spectrum that we're talking about. So here's these two narrow peaks. I think it's maybe the set factor of 7 is different in these. I forget what it is, but you can see these are quite a bit narrower than the signal, which is in the pink. And so we have a very broadband signal in this case where it sort of spans the two Autler-Townes peaks that we have. And for optimal efficiency, which we've calculated, you actually want the width of your signal, full width half max, to actually be equal to the Autler-Townes splitting. So that gives you optimal efficiency. And the sort of dynamics are the ones that I've showed you earlier. So you have your photonic coherence, sorry, these are in different order again, establishes your polarization coherence to spin and back and forth here. And so this is the kind of timed rephased memory here, or the on-demand version here. So the difference between EIT and Autler-Townes splitting is really the emergence of this coherence, and also this sort of rephasing kind of behavior. So the mechanism is quite different, although in the lab, it's just a matter of turning the knob on your laser frequency. And literally, again, that's actually what happened in the lab, is we just kept cranking on that frequency until we ended up in a slightly different regime. The question that people were interested in is, could you be in this regime of EIT? Can the mechanism of EIT work even in the broadband regime? And we think some experiments have probably sort of gone into this regime without really noticing it. So you can have an EIT window that is very large. And what do I mean by EIT? I mean, well, where the slow light phenomenon is the mechanism that's creating the memory. So you can have a very broadly split, this could be it's Autler-Townes splitting, but if your now density, so the other axis that I haven't really pointed out here is the optical density. So here it's about a factor of 100, but here if you crank up your optical density, your slow light depends on your optical density. So if you have a very high optical density, you can get enough slope on your dispersion to slow your light down enough, even in this sort of broad Autler-Townes regime, to get an EIT-like memory in the broadband regime. So you can see we've done these calculations that you get this slowing down of the light, very little. There's a little bit of polarization excited here. Just because we didn't split, should have split these further in order to get no polarization, but that slows things down even more. And you can do this on demand kind of memory. And so in that sense, it is a continuum. I think, Bill, you had the sense that you can go from EIT to ATS, and it turns out you can do like a mix where you get both the slow light phenomenon and the rephasing kind of are both happening at the same time. It's hard, you could probably come up with a metric that said how much is which. We didn't really go that far into it, but yeah, in the lab, it's how much, so basically your Rabi frequency is just the laser power that you have on this control that sets the width between these Autler-Townes peaks. The advantage of using the ATS memory over the broadband EIT memory is just that you can get away with less power and get a more efficient memory. So you don't need as much splitting, and you also don't need as much optical density in order to get the same performance of your quantum memory. And so the message that we wanted to sort of give out here is that, okay, EIT is the memory that a lot of people think about and know, but if you understand the mechanism of the memory, you can actually have fewer resources and a better and more efficient and more broadband memory than just turning up your power and getting a really high optical density for this kind of memory. So
it sounds like in both extremes of EIT, you're working in a low loss regime.
Yeah.
When you are in the Autler-Townes regime, you've got lossiness, but you've gained something else.
That's right. So you've gained speed.
And how much you want to give up.
That's right. I think that is actually my next slide is also, you're so good, Bill. You trained me well, I guess, to anticipate your questions. That's really what's going on here. So this is sort of the overall efficiency versus optical depth. So optical depth is, of course, a resource that is a little bit harder to get, right? It means how many atoms you have to get, how cold they have to get, or if you're working in a warm atom, this actually applies to warm atoms as well. So you can have a hot vapor cell with a high optical depth as well. So this gray curve is basically the best efficiency you can get in any scheme. And this is a universal result, again, from those sort of mid-2000s papers. But you can see here that these blue curves are the performance of the ATS and the red curves are the performance of EIT. So the advantage of this ATS is it's very independent of optical depth. And that's because it's sort of this, like it's that rephasing behavior where it's sort of individual atoms. And so the efficiency one can get is it jumps up really quickly with optical depths. You can work with very low optical depths, but it saturates. And that saturation from unity to some level, 80% or whatever, is what is the bandwidth as compared to your spontaneous emission lifetime. So, because we're actually exciting things, there's actually amplitude in that excited state, and there's going to be some dephasing, some loss that happens because of spontaneous emission. So how much spontaneous emission are you willing to live with? Versus, how fast you want to get. So as you keep cranking this bandwidth up, that's splitting those EIT peaks further and further, so you can kind of climb up this curve. And the question is how far do you want to get? The thing with EIT is that it can be perfectly efficient as long as your optical density is high enough, because you just can get away completely from that from spontaneous emission, but it demands a high optical depth and actually demands quite a bit of power as well. And then the other way to think about it is in terms of bandwidth. So what is your efficiency versus the bandwidth as compared to your spontaneous lifetime? The EIT for low bandwidth, that is a narrow spectrum signal that fits in that transparency window, it's very high. But as you're, given some, I think there's a limit on optical depth in this calculation, the efficiency of the EIT drops off because it is so demanding of optical depth, whereas the efficiency of this Autler-Townes can be high for higher bandwidths. But you see that it's actually, you have to kind of optimize the bandwidth of the signal. So only at certain bandwidths is it going to be perfectly efficient. So there's some timing that has to happen with the Autler-Townes in order to get this high efficiency. So yeah. So that sort of, I wanted to address the ATS versus EIT. The answer is it is a continuum. There are different mechanisms on the different limits, but you can probably work somewhere in between as well. Again, this is sort of the same message. I'll just skip over that one for now. So, yes.
Can I think of this Autler-Townes, like if it were not resonant, then this would be doing like a Raman transit thing, and it's that as you get closer, you can still make it work and use a lot less power.
Correct. So the question is could you work off resonant? And if I just, these two could be off resonant. So there is a group, there's a protocol called the off resonant Raman memory, and maybe you're familiar with. Ian Walmsley's group has really done a lot of work on this in the past 10 years. So it can be very efficient as well. It has a lot of the character of the EIT, but you need a lot of power. And the one thing about it is there's a lot of four-wave mixing noise because you have these off-resonant transitions that can actually basically take you backwards. So if you're trying to, your control beam can actually act like your signal beam. So you get a lot of noise in the off-resonant. The advantage of working on resonance here is that we can mostly eliminate that kind of noise. Any other questions? See what my time is too, because I could probably just talk forever. So the other aspect of this memory that I've kind of glossed over is that it is a collective excitation of atoms and not just a single atom. We've sort of been talking single atom physics so far. And so we say it's called a spin wave memory, and this is the sort of sense in which it's a spin wave, is that at the sort of single photon level, we're exciting one atom into the auxiliary state here, but we don't know which atom in our ensemble, and so we get this collective state. But there's also this aspect of spatial structure here because we have two beams, and the probe and the control here that are interfering, and based on sort of whether the amplitude is high or low, where those are interfering, we'll get a transition or not. So you get the spatial structure built in as well. And so I kind of contrast some kind of cartoon of that. So where you have your probe and your control coming in, and they're at slightly different frequencies because we have this detuning. In our case, it's the 6.8 gigahertz hyperfine splitting for rubidium. And so that gives you some spatial structure, even if the atoms are coming in collinear. And so you can kind of think about, in the regions where there's perfect deconstructive interference, all of the atoms are always in the ground state, and then where they constructively interfere, there's more probability of being in the in this S state. So this leads to the sort of spin wave structure. And if you have an angle, which you can, and we do, between your control and your probe beams, then you get sort of these interference fringes become closer together, and you get these shorter wavelength spin waves. And that becomes important when you want to think about storage time, because there's still going to be some thermal diffusion that can erase the structure. And that is actually one of the limiting factors on how long one can store information in these spin waves. And that's one of the reasons why cold atoms is nice, is because thermal diffusion is largely limited in these systems. Yes.
So with the usual EIT thing, one of my pictures is you have a pulse of light that's your information coming in that is spatially quite long, and then it hits this medium and slows down, spatially narrows, and then you drop it in there and turn it to a spin wave. Let it sit there for a while and then release it again. Yes. Slow speeds up and moves. So in this sense, where you don't have a great slowdown going on, how do you store a whole pulse? So
it's I guess we think of it getting absorbed at the front, and then it keeps going in and keeps getting absorbed as it comes in. So we actually see that the storage, I don't think I have a plot of this, but the spin waves aren't equal like this. It actually, most of it's at the front of the cloud, and then it sort of trails off towards the end of the cloud. Another thing I'm sweeping under the rug here is that for optimal efficiency, you actually want to do backwards retrieval, where you basically completely time reverse the process, so that with the light coming back in is slowly absorbed, and then at the end gets reabsorbed, and that will give you the same pulse back out as the one that you put in, but it'll be in a mode that is 180 degrees opposite from the one that you started with. So maybe the next thing I'm going to say might actually address your question a little bit as well. It's easier to think about with this structure, is that one can actually think about this process a lot like classical holography, where you have two input beams coming into a medium. You're imprinting their interference pattern as a phase, and you can think about the sort of gas as a phase plate. And so the retrieval process is when you take one of your, say, what we might call the reference beam in holography, and send it in. It diffracts off of this phase grating that you've imprinted on the gas, and due to phase matching conditions, the light that comes out is exactly mode matched to the light that came in the first place. And so, yeah, you can kind of think about, yeah, from a very classical perspective, this case. And so this mode matching is important, and it's a nice feature in some ways, because it means that, you know, you always know where your light is coming out. And I think I've been thinking a little bit about not just quantum memory, but as a photonic processing, you know, medium. These spin waves can be very nice because you don't need a cavity necessarily. You have a directionality to the light that is being emitted, which might be useful for, you know, coupling a cold atom quantum computing tweezer array or something to a fiber if you want to get your light out eventually. But anyway, so this idea of a hologram, so that sort of gives you the flavor of why the light that's coming out has the same spatial structure and timing as the light that had come in originally. So that's the end of my sort of model. We can talk about the experiment a little. So it's just a photograph of our coils. So there's a glass cell with a cold atom gas in the middle there. For our first experiments, we just used a MOT, I guess an optical molasses, a very modest optical depth of only about 3. And the power that we're using is also, so 3 milliwatts for the control and 3 microwatts for the signal, just to give you some sense of what we're doing. And these were the first experimental results, so we could send in our input pulse and then get this sort of revival back out if we just leave the control on. And similarly, if we interrupt the control and turn it back on, we'll get our pulse back, and we can do it with pulses as well as Gaussian. So you can see our efficiency is not, you know, super good, and partly we're limited by this optical depth. We're also just using AOMs to turn on and off, so we don't have really sharp edges, but it's pretty good. And actually with the Gaussian sort of pulses, we can make things look a little bit better. We also did this sort of at the single photon level, so we don't have a true single photon source. We just use a weak coherent source by turning our laser down. One thing I wanted to point out here is that we're using single photon detectors, and so we have our control beam coming in on the blue here, and we have our signal is, control is red, the signal is blue. We actually moved the signal, or sorry, I guess opposite. The control is blue and the signal is red. We've moved our control to a large angle for these experiments so that it would not be leaking into our single photon detectors. And so this gives us low noise for the output, but the payoff is that we have that higher, the grating of the spin wave is much finer, and it limits the storage time as a result, but we get very low noise. So kind of a trade-off there. But we can do these sort of single photon level experiments where we now, you know, we're looking at histograms instead of pulses on an oscilloscope kind of device, but we get very low noise here. So these are just looking at, you know, how much light we get out with, you know, without any atoms there, and then without the probe there. And so our signal to noise ratio is something like 40, which is much, much better than, say, these off-resonant memories where the signal to noise is a few typically. The other kind of cool thing is that this is not necessarily just a memory, but you can think about it as doing kind of cool processing. So one can think about the memory process like a beam splitter in a way. So you sort of think about the beam splitter operation as flashing a control pulse on. So you start off with a signal coming in, say that's your photonic light coming in, and then by turning on the control, you transfer the input signal into a spin wave, and you could do it vice versa. So once you've got the spin wave stored, you do the control pulse, and that turns it into the electric field out. So you have this sort of reversible process, and we can sort of think about storage as the beam splitter in turns into a spin wave, and then we get the signal out. So that's fine. That's just storage. But what's interesting is that you don't have to do a full output pulse. So this comes back to this idea that it's a pulse area operation. And so if we have our control sort of start out as weak, we can sort of have it like a quarter to start, and we can have our output come out in 4 different time bins. And these are single photon measurements. So really we're sending a single photon in, and we pulse it 4 times out, but we don't know which of these 4 time bins it's coming out in. So this is a way of having time bin encoding, or you can do the reverse process to do time bin processing of signals using this method. So I should say this kind of beam splitter was, the Raman memory group had done this first, and we were able to do it also with this ATS.
The reflectance is determined by the pulse area.
Correct. So the question is, reflectance is determined by the pulse area, and that's right. So you can just think about, we wait till that spin wave turns into the polarization coherence turns into the spin wave. If we just wait less time, that reflectance is sort of determined by how long we let that happen for. Or you can think about the sort of area of this pulse as as setting the reflectance. So it depends on how much is there before. So you have to kind of, the final one is sort of 100%, right? Because we're getting all of the spin that's left in the system out, whereas the first one is a quarter and the other ones are somewhere in between. Okay, and then we also did this work with Bose-condensates just to sort of work on that coherence time so that they could be colder. And so we found some temperature dependence to the efficiency of storage. So as we get colder in the microkelvin kind of regime, the efficiency gets better and better and better. And that's because our optical depth is increasing. So we get more absorption and it's more efficient. However, at some level that drops off dramatically because actually the condensate, well, we probably are losing density at the final stages of our evaporation, and the gas is actually just becoming really small. So we're losing absorption that way. And then we can, so that you can see the density is changing, but we're still able to work at the single photon level, even with the condensates, which are quite small. So this is sort of the problem that's happening at this low temperature, is that when the atoms are hot, they're big. When the atoms are cold, they are small, and our beam didn't get that small. So we found that by making the beam smaller with these red points, we were able to get more absorption. So we're still at 25 microns. We're not getting small enough really to be fully absorbed. So we need better optics and maybe even a smaller vacuum cell to really be able to focus the light onto the BEC properly to get it all absorbed. So that's, or make our BECs bigger. So that's kind of the limitation here. But we did see that the storage time was quite dramatically improved. So I didn't point it out earlier, but our initial results were only 200 microseconds of 200 nanoseconds of storage. Now we're into the sort of 15 microseconds. So the coldest atoms, this blue curve, it's obviously not going far enough, but we can think it's greater than 10 microseconds of storage here. And the other interesting thing that's happening, this is a bit of a detail, but we can see sort of revivals in the output efficiency if we have a magnetic field on. So we actually see different, we're actually doing the storage on all of the magnetic sublevels. We try to go to magnetic field 0, but if we actually purposely go to some magnetic field, we can see dephasing and rephasing of the different magnetic field sublevels and these revivals happening, that where the fall off of the storage time, if we go to the 0 field, it sort of follows the peaks of these revivals. So that's also possible, but there might be some, there still could be some magnetic dephasing, and there might be a way to sort of get better dynamical decoupling pulses or something that would help us sort of extend that lifetime, do that magnetic dephasing, which we think is probably a dominant source of the storage time here. And so I guess we basically, we see very good signal to noise up to, hundreds, when our mean photon number gets, up to 1 for the weak coherent pulses, but that means we probably have more than 1 photon in many of our pulses, but very high signal to noise ratio in this case. We can predict that if things were better experimentally, how would this memory do? And maybe this is, the important graph is this one on the bottom. That is, if we get colder and colder, we expect the memory lifetime to get into this millisecond range, where it becomes a very practical kind of memory. The limitations are going to be recoil motion. So I didn't talk about it, but actually, that spin wave is going to start to drift because of the momentum of the light that you've transferred to some of those atoms. And also inelastic collisions will eventually limit your lifetime here. but it should be good. The other interesting one here is the noise difference between an EIT protocol and an ATS protocol, where you're asking for the same efficiency at the same optical depth. And the ATS is sort of orders of magnitude lower noise because it is using less power. So you have less control, you can get away with less control power, and it's really that control power that's driving off resonant transitions and giving you the noise. So there is some advantage to the ATS protocol in this sense. All right, yeah, I keep talking about the memory. So the most recent thing we've done with the memory is to try to make it even faster. And one of these ideas sort of, again, comes about from these early papers, was to really use this idea of superradiant emission. So can we make the atoms emit not just with their spontaneous emission lifetime, but do this collective emission due to their collective effects due to superradiance. So here we want to do things even faster. So we want to sort of do this excite and then shelve them and then unshelve and re-emit. And we want to do that with the superradiant kind of timescales. So the protocol basically is that you want to do this time reverse process. You want to absorb the light with the sort of reverse of the superradiant emission that you would expect. So this is because this is the most efficient thing to do. So you turn on your light sort of an increasing exponential, and then you do a pi pulse where you take your excited state and you flip it into the ground state very quickly. And then once you, I guess if you turn back on that pi pulse later, then it should emit with the superradiant emission time. So you can see these timescales are very much shorter now than the spontaneous emission life scales spontaneous emission lifetime. So yeah, it's just sort of asking the question, can we do things faster, or are we going to be fundamentally limited by this spontaneous emission lifetime? And the answer is you can do the things very fast, but these pi pulses are very demanding. They're very short, so it means you need a lot of power. And short pulses sort of push the limits of the EOMs we have. So we did show in the lab that we can do this sort of this is an attempt to do the exponentially increasing pulse on. We have a tail. Unfortunately, can't turn it off quite quickly enough, but we do see that the emission that we get from our atoms is faster than the spontaneous emission that would be given by this black line here by about a factor of 2. And we can use this for memory, so we can get very short pulses of light out, but it demands a lot of control power. So I'll just sort of quickly go over that. So this will wrap up my talk about the memory. So I think there's a strong outlook. The next steps are really working with quantum information, which we haven't done to date. So how are we going to encode information? Like I mentioned earlier, maybe polarization or time bin encoding. And we want to move more and more towards this quantum optics. We're also thinking more about how to do more practicality with multi-mode storage. There's ways to do that with the spatial degrees of freedom and also different frequencies. And also thinking about practical implementation. So how do we take our 2 optical tables and make a cold atom memory that could be more portable? We could spend a lot of money and just buy something, or maybe there's a better way to do it. We have some collaborations in Canada we have a Canadian quantum satellite, which is going to operate at 780 to 795 nanometers, which for rubidium is very convenient. And so we're thinking about experiments like get 2 photons, send one to the memory and one to the satellite, and show entanglement between ground and satellite, which the Chinese groups have also already done, but that's sort of the first steps towards this path. So there might be opportunities, with cold atoms, maybe with warm atoms, to do that kind of work as well. All right, so I don't have a lot of time left. I have 3 different topics I could talk about. So I'll breeze through some of the other work in the lab, but I'd be happy to talk about it later. I'll just give you a bit of a flavor. So we've done some, as I mentioned, quantum state control with the Bose-condensates. One was to look at a qutrit ensemble, basically just going from 2 states to 3 states of a quantum state, and we used the condensate as sort of a full qutrit. So we just used 3 levels in the ground state of our rubidium, 2 of them in the F equals 2 and 1 in the F equals 1. So we actually just used microwave control. And a large motivation for this work was actually to learn how to do this kind of microwave control using a fancy arbitrary waveform generator to do it. And so, yeah, we can do the BC. And the nice thing about these measurements is you have an ensemble measurement, basically doing single atom physics here, but we do many, many copies. And we do Stern-Gerlach imaging to measure the final states of the system here. So basically, the upshot of all of this is that we're able to show that for specific timing, you can do direct, I do have my figure here, not really, but you can do basically direct coupling between the 0 state and the 2 state without any population in the 1 state. So using only 2 couplings, we can do full 3-state control of the system. So skip over that. The fidelities were not great, sort of a 90%, 95% level. And we think that was actually due to dephasing because we were optically trapping these atoms while we were doing the experiments. And probably just even going to time of flight might make better fidelities than the ones that we had here. The other recent work that we've been looking at is doing holonomic operations using Bose gas, and the idea behind this is it's a kind of geometric phase that if you take one path through phase space, it would be a different operation than taking a different path through phase space. And the motivation for this is that it might be more tolerant to imperfections in the system than a dynamical gate where you're relying on timing instead of geometric phase. And one thing that would be nice in this kind of system is to look at non-abelian rotations where taking one path through space gives you the possibility to get different I like to think final states. So in the case of a degenerate system where your system is degenerate, you can get coupling between these degenerate states where one loop through parameter space can maybe flip your spin or flip your state from one to the other. Whereas a different path would give you a different final state. So again, just in the interest of time, I've just said the same thing. Well, I guess you might get some intrinsic fault tolerance where the path of the loop matters, but not the speed it took. But there's some recent work, and including ours, that shows that it's actually, there's no free lunch, that the dynamical, dealing with any dynamical noise still plagues the system more than we actually originally anticipated. So the approach we took to getting degeneracy in the system was a Floquet driving, and it's based largely on this work by Gediminas Husliunas in Lithuania. And this nice quote from his paper about why this works is that the degeneracy of the Floquet bands comes because basically you're driving things periodically. So on average, everything has 0 energy is kind of the idea of why Floquet driving gives you degeneracies. And so the nice thing is, with cold atoms, we can do this, but really this is a method that could apply to many different kinds of quantum systems where you can build in that degeneracy in this Floquet limit. So for us, it was 3 levels of the ground state of rubidium where we coupled them together with RF, and using the parameters of the RF as our parameter space, we can change the amplitude, and the detuning basically gives us the two parameters that can be in our parameter space. So we can go into the Floquet basis, these 2 angles. So tuning between sort of coupling in the FX and FY versus the FZ gives us that parameter space to do different loops. And so the 3 different loops that we did sort of in that parameter space are all the great circles, the orthogonal great circles on this block sphere. The measurement is just, again, these Stern-Gerlach measurements where we're doing, again, single atom kind of physics, but on ensembles. So we get measurements of many copies of the same thing. And we basically, prepare a BEC, do a loop operation, and then to do tomography at the end, we do resonant RF pulses to look at different projections of these states to do some tomography. So this is an example of some data where you start with all of the atoms in, say, the MF equals 1, you do a full loop through 2 pi and you end up in a different state. So that's the basic sort of rudimentary thing, is that you've done this loop, and because these states are in this degenerate subspace, you end up in a different state than you started out with. You might say, well, that's trivial, you just did things badly, but we've, it matches our theory very well. This is in not the Floquet basis, so you can actually see the Floquet oscillations here. So this is what we're looking at. And so our final measurements show that we're able to create these sort of superposition states that we can predict. And by varying the phase, which is shown here, of the RF, we can kind of see different cycles of that. So we are doing this coherently. We can do it in the F equals 1. This is what I just showed you, or actually in the F equals 2 basis, which is even more complicated. But the problem was that even small detuning drifts, so slightly different implementations with slightly different detunings, quite dramatically affect the fidelity. And so what is happening here is that there is a term that is not being Floquet driven. It's just a static slightly different magnetic field in each implementation. But when you go to the Floquet basis, now you have this sort of noise, which is a dynamical phase that comes into your system. So, we can do the full modeling, which shows that if we take this into account, we're doing what we think we do, but we don't necessarily, we're sort of fitting to this detuning in each implementation. And so, so we understand we're doing the right kind of, there is definitely this sort of non-abelian flavor to what we're doing. It's just that this noise creeps in more dramatically than we originally anticipated. So actually, this bottom graph is maybe interesting here. Is that just the scale of of that noise has to be maybe less than or around 1% of the Rabi frequency. So that's just the other limitation, is how strong get stronger RF and do things a little bit faster. That might also help on the scale of the noise. So we do see this non-trivial state evolution, but we're still very sensitive to detuning drifts. And there's actually an interesting theory paper about a year ago, I referenced on a previous slide, that showed that in these holonomic systems, you think you're overcoming this noise by getting rid of the dynamical noise, but actually it shows up in just the same way in this Floquet basis. And so it's maybe unsurprisingly, it's just really hard to get rid of. But I think we've done this in cold atoms, and there's sort of a question: is there other systems where this might actually work well? And then actually I was talking with Ian this morning, like there's more of this sort of dynamical decoupling. Is there better control sort of pulses that are not just simple loops that could, is there more complicated loops through parameter space that might help us overcome some of these issues? And the final thing is, yeah, I won't really talk about this, but we also work with warm atoms and microwaves, vapor cells inside of sort of macroscopic microwave cavities that gives us some nonlinear optics. It's kind of fun. So most recently, this is what we've done, is just basically we apply microwaves and light at the same time, and then we generate light on the third transition in these warm atoms. And the nice thing is that with the Doppler shifts, you can actually generate light over many different frequencies. So that's been fun. And let me wrap it up. So we've done a lot of work in neutral atom atomic memory over the last many years. These protocols provide broadband, fast, low noise, efficient, and in principle, long-lived photonic storage. So I think there is some promise here. We've been working towards quantum state control and also these warm atoms and microwaves. And let me just finish off by, again, acknowledging the work of many people who have worked on this over the past many years. So thank you all.
Are there further questions for Lindsay?
So for your superradiant memory, have you thought about putting cavity? That's another cavity, like cavity or hollow.
Yeah, so the question is, have we thought about putting a cavity with a superradiant memory? Practically, no, we don't want to really work with cavities necessarily, but it would, basically the cavity would enhance your optical depth, right? And so you would get, the more optical depth you have, the faster, so your superradiant time depends on optical depth, and so that would enhance and make things faster. So yeah, as a it would be better, I would say, but also just technically difficult, so yeah.
So in sort of writing quantum information to your memory,
Mm-hmm.
you talked about how time-bit qubits might be
Mm-hmm.
interesting. My question was, when you can separate your quantum information to early and late,
Right.
and you store your early with your control beam,
Mm-hmm.
how do you deal with the problem that when you go to store the late bits, you don't read out your early spin?
That's a good question. I think that, yeah, it would come out. You're right, like in the sort of beam splitter picture. You might actually, yeah, I hadn't thought about that before. That's a good point. They do it in the AFC memory, but I think they shelve things, so you might have to do the same thing where you would have to do an additional shelving step. Yeah. And we don't address any of the Zeeman structure to date, but I think we could, and that might actually help us there.
Could you go back one slide?
Yeah. Oops.
It was sort of a summary.
Yeah,
where
there it
right,
is.
right.
Yeah.
So I realized that I didn't understand the difference between readout and recall.
I use them interchangeably.
Oh, okay.
So yes.
The superradiant memory,
Mhm.
there if you use exactly the same wave packet of the incoming.
Yes.
Right, as a signal that limits the output of the superradiant.
Mhm.
And then I noticed that beforehand you mentioned that the absorption is in this direction, emission in this forward direction.
Yes.
And now in that case, I noticed that the arrow was backward. Does it have to be in such a way that it satisfies the time reversal or?
It should be. So the question is, yeah, with the super radiant memory, I was showing forward absorption and reverse emission, reverse recall. Call it in that case often or readout. And in the previous one, I showed forward absorption and forward recall. In both cases, the ideal situation is to do backward recall, and that it's because of that time reversal. So even in the ATS, the optimal situation will always be to time reverse your process. It's just practically it's harder to do in the lab. There's this number, which is 54%. So you can, the maximum efficiency you can get on forward recall is 54% efficiency. And so, yeah, to get to this 100, you always have to do backward recall. And that's because that basically you want to think of this as a, yeah, a time reverse process. And so you just want to put everything in a mirror and go backwards. Yeah.
Any further questions? All right, well,